Hi, everyone. Welcome back. I think we're going to probably be able to finish out this this section 5.5 in this third and probably final segment here. We've done a lot of things so far that well, first we proved the trigonometric identities for some double angles. Then we worked out some, what I would consider somewhat to be application problems where we know certain things, certain quantities, and try to find other quantities. That's basically an exercise to use those formulas. Now, I want to focus just a little bit of attention on some proving some identities using these double angles. So let me just switch over here. And I'm going to start with something that I'm going to make a little bit of commentary, but I'm also going to point out some things that are maybe some ways to tackle these, because this is kind of a new sort of beast that we have. So I think we're on page 7 now. I think I'll probably be able to get through about 3 of these. The first one's pretty trivial, but the other 2 might take a little bit of time, and of course I want you to practice this stuff on your own. So I'm not going to take all that quote fun away from you. But let's do this one. How about prove that the quantity cosine to the 4th power of theta minus sine to the 4th power of theta is equal to cosine of 2 theta. Now that's kind of interesting, because this is basically telling us we have yet another formulation for cosine of 2 theta. But this one, it's pretty trivial, and you'll see why fairly quickly. Now, normally what I would say is that if you're going to try to do a proof like this, the first thing to do is to bust down the argument into something that is a little bit cleaner. 2 theta, you want to sort of simplify the arguments by using identities. However, in this particular case, I don't think that's really the right way to go, because what you're looking at over here is a difference of squares, and so I think that maybe factoring this is a good idea at first. So I'm actually going to start from the left, which is sort of contrary to what I would normally do. So cosine of the 4th power of theta minus sine of the 4th power of theta happens to be equal to the so it's a difference of squares. So you have basically these are squares of squares. So this is going to be the first term, which is cosine squared of theta, minus the second term, sine squared of theta, times the first thing plus the second thing. I think you can see right now why this was a better way to go, because this term here is just 1, and this is actually the first expression for cosine of 2 theta. So this rationale here is just algebra, right? And then so now I'm going to multiply it by 1 times cosine squared of theta minus sine squared of theta. This is a Pythagorean identity. And observe then that this right here is actually a formulation for cosine of 2 theta. And I'll just call that double ID for now, and I'll probably start using even less letters in the future. So pretty quick proof. Maybe let's try one that's not quite so quick, but still involves some of these different expressions. Let's try one. Oh, I've got a number to choose from. I might do more than just one. These are really where you start to develop your skill. But let's take one that's show that cosine of 2 theta equal to 2 minus secant squared of theta over secant squared of theta. Now, I haven't done this one before, so I'm just going to sit here and think about this a second. Again, I would say we should just do something with that, but I'm not entirely certain where that's going to get us. We know we have several expressions for cosine of 2 theta, and so that's why I'm saying that there's not just one, and so it's hard to say which one to start with. One might work really well, but then another one might not. But what I want you to notice here is, remember those tactics we've used before where when we have functions that we're not super familiar with, that we maybe turn them into sines and cosines and see where that leads us. So I think that might be the strategy here. So first off, it makes sense to split these apart maybe, and then I'm actually working with 2 different fractions because I think I see some simplification going on here. So I think I'm going to start on the right. 2 minus secant squared of theta over secant squared of theta happens to be equal to 2 over secant squared of theta minus secant squared of theta over secant squared of theta. And the reason I did that is to kill this off and hope that this does something, which I think it does. So the first step is, this is just an algebraic step. And I'm going to do one more before we do any trig. Secant 2 over secant squared of theta minus 1, also an algebraic step. This is starting to clean up a little bit. Now, recall that secant is 1 over cosine. So 1 over secant is equal to cosine. So 1 over secant squared is equal to cosine squared. We're going to end up with 2 cosine squared of theta minus 1. And that is a reciprocal identity. Now notice this is the so-called third version of cosine of 2 theta. So this is just simply cosine of 2 theta, and that's a double angle identity, right? So I didn't really know the solution to this starting. I just kind of said, well, let's just keep banging away at this until maybe we find something that looks recognizable. Again, the reason I didn't start with cosine of 2 theta and turn it into its equivalent is because there's 3 different options, and I thought that might actually create more confusion than give us a way to work with it. But I think I can probably show you a version where maybe that is the right thing to do. And I also want to introduce this notion of, we want to be flexible with these expressions when the argument is not just 1 times theta and 2 times theta, because the real power to this is the ability to double and double and double. And if you use a sum expression, you can triple, and all that sort of stuff. So, but unfortunately, we haven't seen a lot of that. So let me try one that involves exactly that. I think I'm up to page 8 now. Okay, so let's verify. I like that word too. How about we verify? Oh, this one is really let's try this one. This one's a little bit tougher, so might have some more legs on it. So 1 plus cosine of 4x over sine of 4x equal to 1, hold on a second, minus tangent squared of x over 2 tangent of x. I think that works. I kind of took one on the fly here that I've already gotten and said, can I make this work? So there might be some trickery involved here, because notice what I see over here is this looks an awful lot like the tangent of 2 theta, only it's upside down, right? Tangent of 2 theta should be, well, tangent of 2x should be 2 tangent of x over 1 minus tangent squared of x. So this is just the reciprocal of tangent 2x here. These terms over here, well, I don't really know. There might be some way to beat them into that form. But what I'm thinking is maybe we start over here on the right first and beef this up to a tangent of, or 1 over tangent of 2x, and then see if I can't work from this left-hand side and get it to look like 1 over tangent of 2x. So starting with the right-hand side, 1 minus tangent squared of x over 2 tangent of x equals 1 over tangent of 2x. And that's just a double angle identity, right? So now, starting with the left-hand side, I want, 1 plus cosine of 4x over sine of 2x, oh, sorry, 4x. Now, what my target here is now this. It's 1 over tangent of 2x. Before it was this crazy thing, but since I've already sort of gone a little bit of the way there, I'm gonna now try to turn this into tangent of 2x, which there's many ways I could have that. That could be sine of, 1 over tangent 2x. So that could be cosine of 2x over sine of 2x is one way, or some other form that looks like that. So here's where that advice to take this and bust this up makes sense. So first off, recognize this is 2 times 2x. So the formulation for cosine of 2x, we could actually use like a cosine of 4x, and the argument becomes 2x. So that's not all that unusual. But let's see what this looks like. So let's use some double angle formulas. And with cosine, I have some choice. What I'm going to use is actually the third one, because I think it's going to make things, I think it's actually going to make things clean up a little bit. Okay, so I have 1 plus the quantity 2 cosine squared of 2x minus 1. That's in the numerator. And in the denominator, I've got 2 times sine of 2x cosine of 2x. Those are all double angled. Now notice, all that really happened here, I mean, because there isn't really a formula for 4x, we can create one. And in fact, I argue that's actually what we're doing, is creating a formula for 4x's or 3 or whatever else. But really, it doesn't matter what's in here. The key is that this quantity is half that. So if this actually started off as something like, I don't know, 16x, this would be 8x, right? That's sort of the key here, is you've got to have a little bit of fluidity in terms of these arguments. But anyway, so now that we have this, the numerator is going to clean up to 2 cosine squared of 2x all over 2 sine of 2x cosine of 2x. I mean, this is just simply some algebra. And then notice we've got some cancellation. The 2 will cancel, and one of these terms of cosine 2x will cancel. So we're left with cosine of 2x over sine of 2x, which is just an algebraic cancellation. And this cosine of something over sine of something happens to be the cotangent of that something, which this is a quotient identity. And then we're going to get to where we could have gone a little bit further from the right-hand side, but this is where we're going to get this 1 over tangent of 2x by a reciprocal identity, and this is the target. So from here we went right-hand side 1 step to something that looks a little simpler. Then left-hand side to the same thing. So this proof then is all done. Okay, let's try, I've got one more. I don't think I've gotten too long on this. And this is, since this is kind of the last one, I want to show you this problem is actually a little bit challenging. Well, it's not really challenging, but I think there's a problem in the homework that's very similar, and maybe the instructions don't make perfect sense. So I'm gonna go through this, and it is kind of a little bit of a trick. So find cosine of 3 theta in terms of cosine of theta. So what does this mean? Remember when we said things in terms of other things? It means that what we should have is at the very beginning, at the very end of this process, we should have cosine of 3 theta equal to something that involves cosine of theta and maybe some coefficients or some constants, but no other trig functions. That's the goal of writing cosine of 3 theta in terms of cosine of theta. And there is a little bit of a trick to get started because we haven't worked with these odd coefficients on these arguments yet. But no, this is going to, the trick here is to either break this up into a sum or a difference. And so I'm going to go with a sum because I remember the sum form is a little bit better. So starting with the left-hand side, cosine of 3 theta. This happens to be equal to cosine of theta plus 2 theta right now. So I'm playing around inside the argument. And recall from the sum formula for cosine, that is going to be equal to the cosine of the first thing times the cosine of the second thing minus the sine of the first thing times the sine of the second thing, right? Just kind of using that A plus B formula. Now my goal is to bust everything into terms of cosine of theta only. So what I would suggest is to work on the arguments first and then see if there's obvious ways to clean it up. So this, and since I'm already trying to get, well, I'm not really sure what's going to be the best way to start here, but I'm going to go ahead and write this one out as the version that has only cosine, so so-called third version. So this becomes, it's going to get kind of long here and then it's going to trickle down into something a little cleaner. So cosine of theta times the quantity 2 cosine squared of theta minus 1. Okay? And then this other term, we don't really have much choice since we've only got one real expression for sine of 2 theta. So this will be minus sine of theta times 2 sine of theta cosine of theta. Kind of ran out of space there. And now maybe just clean things up a little bit. So I have two terms here. I'm going to distribute this. So I end up with 2 cosine cubed of theta minus cosine of theta minus 2 sine squared of theta times cosine of theta. Okay, so we're almost there because it looks like this formula, almost every single term is just cosine of theta. Now with some powers and maybe some coefficients, we got to do something about that sine squared term. So we're going to find a substitution that only involves cosine of theta. We have 2 cosine cubed of theta minus cosine of theta minus 2 times 1 minus cosine squared of theta times cosine of theta. Okay, so I've made a Pythagorean identity substitution here. Now let's let's distribute this term as well. So we have 2 cosine cubed of theta minus cosine of theta. And then the first term is going to be minus 2 times 1 times cosine. So I have minus 2 cosine of theta. And then the second term is going to be minus 2 times minus cosine squared. So 2 cosine, positive 2 cosine squared times a cosine, which will give us cosine cubed. So plus 2 cosine cubed of theta. And now just start combining like terms. We have 2 cosine cubed theta here, 2 cosine cubed theta there. So we end up with 4 cosine cubed of theta. And then here we have a minus cosine theta minus 2 cosine theta, which actually be minus 3 cosine of theta. So have we achieved what we wanted to do? We have the cosine of 3 theta equal to an equation that only involves cosine of theta and powers of cosine theta, possibly with coefficients. We don't have a constant term out there, but I think that this is the goal. So this is kind of a series of logical steps, not terribly difficult, any one of them, but it's kind of this process. And like I said, this is kind of key to something that we will never do, but algebraically, to being able to divide an angle into three. The reason we don't do it is because I don't know that in any algebra class they teach how to solve a cubic anymore, unless it's just sort of a special case. So anyways, I think that's a very long-winded explanation of this problem. This is the last, I think this is the last segment I'm going to do for section 5.5. Just understand that I intentionally did not do any of this so-called product to sum and sum to product identities. They're a little bit tricky, and I don't know that they have a whole lot of utility. You may see them in some far future in a Calculus 2 class, but the prospect of because we don't emphasize them very much, and the prospect of remembering them, as much as a year or even 2 years from now, seems kind of remote. So if that's one thing that we end up skipping, it's not gonna bother me too much. Okay, well, we will see you in the next section.